test. Okay? Okay, we're live.
We are live?
We are live.
Ah, awesome. So, hello and welcome to the first Linz Rust meetup, which does not happen purely online. We are meeting here. Woo! That's really a premiere for us, and we want to thank the Grand Garage here in Linz for hosting us. We are here at the Sun Deck, which is luckily now a shadow deck, so we see a little bit on the screen. I promise you it will get better. The longer the evening, the more beer we have. No, I'm not saying that. It will be better. And now we will kick off today's Rust meetup with some community news, shouldn't we, Stefan?
We shall. So, first of all, this is brought to us by the calling. So actually, and I guess this is part of the whole PowerPoint karaoke thing. The community news come at the very last. So let's do everything else first. Sorry, we are improvising that. But I guess one thing that we need to mention is that this is our anniversary edition. This is the 12th Rust Linz meetup. So we are doing that now for a year, and I guess it's just really nice that we can celebrate our first anniversary together with you, like in person, with some beer, with some cake, with all the safety measurements that we do, that we are outside on fresh air. Yeah, and since it is our anniversary meetup, I want to introduce you to today's speakers. That's me, and that's Rainer. So, so I'm going to talk about serverless Rust in a couple of minutes, and afterwards we are doing a little break, and then you are going to talk about traits. So
you forgot the most important thing. During the break, we will have a cake, a very, very special birthday cake. So stay tuned. You will enjoy it. I'm very sure.
Well, if you are virtual on the internet, you can join us on Discord, post some comments there. We are going to monitor that. So if you have any questions and want to ask them on Discord, you can do that. That's for the folks in the internet. For the people here live, you can also ask via Discord, or you can ask us in person. This is weird. You can try that, asking questions directly. Let's try it out and see if this works. I'm pretty sure it does. We have two sponsors who make this possible today. One of our sponsors is the Innovationshauptplatz Linz, and the other one is Dynatrace. They too helped us to get our anniversary meetup going. And now the communities are up. So this is your part.
Yes, thank you very much. Thank you very much. The next slide, this one is very near to my heart. It's about Linz Codes. This is an event that we do here in our hometown Linz, and this will be a twofold event in August, 6th of August and 20th of August. Essentially, we are inviting kids between 8 and 18 years, and we are going to program at the Danube River under the Lentos Art Museum. It is an awesome location. Everything will be outdoors, so we are sure we are safe from COVID and so on. So if you live near Linz, Google Linz Codes or go to our website linz.codedojo.net. You will definitely find a link there. You can get a ticket, and we welcome kids, and we also welcome software professionals who would like to work with our kids and do some mentoring work. It's still my part. The Coder Dojo will not only happen in person during Linz Codes, but the Coder Dojo will also happen virtually as every Friday tomorrow. Tomorrow will be virtual workshops like every week that here in summer.
Yeah, and then we have two more things. One is we have socks. Socks with cats on it. So if you need socks, come to Rainer or to myself. We have them up there. And get some. And we have a photo of the most amazing cake. I don't want to spoil it for you. You're all getting cake, but for the folks over the wire, that's the most perfect cake in the entire world. So
isn't that awesome? Isn't that awesome? We will have this cake today in the break. This is our, as Stefan mentioned it, our anniversary meetup. So it's the 12th Rust meetup today. And Barbara from the Grand Garage, she baked this cake. It's really awesome, and I think we should all give her a big round of applause for doing that for us. Thank you very, very much. Here she is.
Cool. So, and I guess with that, I'm going to switch slides. Folks in the internet, this is going to be weird because I have to run to the monitor to see what I'm actually doing. But I'm back with you in a minute. And yeah, so it's on. we go. Show this notes in window. There we go, and look at that. Cool. All right. So you folks can see my screen, and the folks on the internet can hear me. Nope. You can't see my screen. Rainer can't see my screen. Rainer is going to see my screen right now, aren't you?
Yes.
Cool. All right. So wow. Meetups are hard. Who would have thought? Again, welcome all of you for being here. That's fantastic. I'm super happy that we can do that. I want to talk today about serverless Rust. So I'm Stefan. For the folks who don't know me, I have the worst Twitter handle in the entire world, but I'm also one of the co-founders and co-organizers of Rust Linz. And over the last, let's say, 1.5 years, up to 2 years, I've done a lot about serverless. So serverless and serverless platforms and cloud providers who provide serverless offerings are what I do basically on a day-to-day basis. That's why I want to talk to you about serverless. I'm going to promise there will be some Rust, but there will also be a lot of cloud internals and things that you might don't know if you're using one of those serverless offerings. So who in here, who out here has not heard about serverless? You can raise your hand. Okay, so everybody heard about serverless. That's great. Usually so let's say serverless comes in a couple of different flavors, and this would be usually the point where I do this particular joke that, well, serverless is not actually serverless. There are still servers, you know, that's old, everybody does that. The thing is, what I think nobody talks about is that there are multiple flavors of serverless, and depending on who you talk to, everybody understands something different. And one thing that serverless is the whole auto-scaling part. That's the infrastructure serverless, where you care about servers less, which means some cloud provider, whichever that is, make sure that all your infrastructure problems are handled. And usually, actually, this is one of the most important points. This comes with auto-scaling and consumption-based pricing. So this is, I guess, the most important distinction between all the other things. You just pay for what you're actually using, be that an entire server that is provisioned, or just, you know, a little bit of CPU, a little bit of memory, and there you go. The other part is more on the application developer side, and this is what is usually referred to as functions as a service. So instead of writing your entire server, HTTP server or whatnot, you don't write the entire server logic. You are just writing this little piece of logic that actually does something. How this is getting called, transferred, how the payloads are handled, how the responses are handled is not your part. You just focus on this little teeny tiny stuff that actually does something. And for some cloud platforms, this is actually often seen as some sort of glue code, especially if you think about AWS. AWS has 270 services or something around in the ballpark. You could basically run your entire application on AWS services. But you need a little bit of glue code to connect the bits and pieces and to make sure that all those services work together. And there are two, so for the auto-scaling stuff, there are lots of examples. One that came up recently is, or that I found out recently, is Google Cloud Run, which is really, that's my Docker file, do whatever you need to do with it, and AWS Fargate. And on the function as a service side, so the two most well-known offerings are AWS Lambda and Azure Functions. And we are going to look at the internal of AWS Lambda and the Azure Functions today. The thing is, consumption-based pricing and just writing business logic or just writing the functions, those two things can be seen totally separate. But usually they are working really well together. Azure Functions has offerings where you don't have serverless scaling, where you just say 100 servers please, and I write functions, but they are running all the time. They are all provisioned the entire time. This is possible. But usually you use them with consumption-based pricing, where I say, okay, I'm just going to pay for what I need, and AWS or Azure is making sure that we just need, that they just provision what I need. Which brings me to the billing if you use the two of them together. So usually most of the serverless providers say, we charge you for the time it takes to execute your stuff and the amount of memory that you need. That's very much simplified, but that's usually a way to calculate it. Calculation of serverless pricing is a hell. There are so many factors involved, and I'm going to get to that at the end of the presentation. There are companies specializing on calculating your stuff. So we are not going down that road. We are going down that road why we want to use Rust with serverless. And if you think about that, the entire pricing model of serverless is you pay for amount of time and for the RAM that you use. You have to say that Rust is really good at memory and speed. So you have really fast applications, and you know memory is everything that Rust is about. It's using just the right amount of memory, not having a garbage collector running, not over-provisioning memory, just having what you actually use and what you actually need. And that's why I think Rust is a really good fit for serverless. Okay, let's look at two functions service providers, two serverless providers. This one, what's that?
AWS Lambda.
Okay, for the folks in the stream, AWS Lambda. Well, no, it's the Half-Life logo, and not everyone is aware of that. So if you see any AWS Lambda blogs out there, they're usually using the Half-Life logo. Even AWS sometimes uses the Half-Life logo in their blog posts. This is the actual AWS Lambda logo, so get this in your brain. If you see that, that's AWS Lambda. The rest is Half-Life. And yeah, of course, we want to talk about AWS Lambda. And AWS Lambda, I couldn't say if it's the first one, but it's definitely a pioneer of functions as a service. So the poster child, one of the services that everybody has in their minds when talking about serverless. And I know it from making web APIs, and the more I spent with AWS Lambda, the more I found out that I guess web APIs is just a side effect. I guess this wasn't planned, that just works as well, because what it usually, or what it actually should be, is just this little bit of glue code between AWS services. And that you have something like the API gateway that does HTTP requests or makes HTTP endpoints that you can call and make requests to. That you can attach a Lambda after that is actually, yeah, that just works. But I guess it's not the main use case, or Lambda was not designed exclusively for that. Lambda is very much unaware of triggers. It just takes an event that can be an HTTP trigger event, yeah. But what it does, it takes an event and it processes some workload and then it produces a result. It's like the classical function. You have some input, you have some output. In the best case, it's serverless. It's not stateless, which is not entirely true, but which is a mental model. And Lambda runs in very, very lightweight micro VMs, Firecracker micro virtual machines. And Firecracker is nice because it's written in Rust and it's a fantastic piece of technology. So if it's open source, you can check it out. There are some very clever things in there. And then you think about AWS Lambda, you shouldn't think about servers that are provisioned for you, where just write the glue code. They are actually workers. And this is a very important detail we are coming to in a minute. So if you're doing AWS Lambda, then I have to make my notes a little bit bigger so I can see what I've written there. Otherwise, it's becoming some sort of karaoke. Or look at that screen. So AWS Lambda, the execution lifecycle comes in a couple of steps, and what you see here in blue are all the bits and pieces that need to be run always, and all the pink parts are those pieces that we call cold start. So what happens when you call a Lambda, or when you start invoking a Lambda for the very first time? AWS does a couple of things. First, it checks if you're even allowed to do that. If you're allowed to do that, it checks if you are within the range of concurrent workers that Amazon can provide for you. And if that all is okay, AWS Lambda requests a worker. So you can think of a fleet of micro VMs, and you can request one of those workers to process your workload. If you get one of those workers, and if the worker is what we call cold, which means the worker doesn't know about what you want to process, the worker downloads some code, spins up or creates a sandbox, downloads the code, your stuff that you've written, and bootstraps your application. If you think about Node.js, this means that downloading your JavaScript files, downloading Node.js, downloading the Node modules, packing them in a folder, and then starting Node with the application and booting it up. And only then are your workloads processed. So this is the typical AWS Lambda execution lifecycle. A couple of the things need to be done always, but they are very fast, except those bits and pieces in the middle, the pink column. This can take some time, and this is the cold start time. If the payload is processed or the workload is processed, and you get another request, only the blue parts are running, which means AWS checks if you're allowed to do that, and if there's already a warm virtual machine, you are processing that code, or Lambda is processing the code. If you look at an invocation diagram, this is how the invocation could look like. You have a trigger, whatever the trigger is. Let's say it's an HTTP trigger. You're getting a yes.
How does scripting work for this cold start? So you have this ICM, pipe tracker, where your workload is going, and you reached the limit. So AWS needs to spawn or take a new worker. Will it be faster than initiating the first one, or?
This is exactly what you're going to see here at the screen now. So, yeah.
Can you repeat the question?
Yeah, I'm going to repeat the question for the chat. How does cold starting micro VMs work if there are many processes running? Can I put it like that? Yeah, this is what we are going to see right now. So what is happening when one of those workers is provisioned? And what happens if you're already running a workload or processing a workload? What happens if another one is coming? So let's say you have a trigger. This can be an HTTP trigger, whatever, just a trigger. And this is the very first trigger that you have, like the HTTP request that you need to process something from a backend. AWS does its cold start thingy, which means requesting a worker, downloading an application, blah, 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 the entire thing. Once your runtime is bootstrapped, the runtime does an HTTP call to the AWS REST API. This is this /next that you can see here in the screen, which means it does a call to the REST API asking for the payload. So it asks, which event should I process? Can you give me all the information that I need to process my event? Once it has fetched this information, it processes it. This is the code that you are writing, whatever that is. This is the one thing that you are doing. Once the result is there, it does another HTTP request to the AWS REST API with a post message to response, giving the result. And during that time, this worker is exclusively working only on this particular workload, nothing else. Once the response has been sent, once the result is finished, the worker asks for another workload to process, for another payload from the trigger, for another event to process. If there's one, it grabs it from the queue, processes it, pushes the result back, and if there's none, it goes into hibernation, which means Firecracker is freeing up all the resources. So it stops, hit the pause button, resources are free, and another worker can get those resources. There's a certain hibernation period. If within a couple of minutes AWS is not open about the period, about the amount of time that needs to pass, but if this happens after the amount of period, the worker thaws again. So you freeze it, then it thaws again, which means it's not a cold start. It's still a warm container, but it gets all the resources back, it gets CPU back, it gets RAM back, and then can process another workload. Now what happens if you're processing a workload, but another request comes in? In this case, AWS Lambda spawns up a new micro VM. The entire thing doing a cold start, grabbing that payload from the queue, processing the workload, giving back the result, and then going into hibernation again. And this is actually the one big difference between AWS Lambda and all the other serverless offerings out there, which is that for every workload that you are processing, you have a dedicated worker doing that. No parallel processes within the worker or something. Not the thing that Node.js is really good at, which means doing I/O and being able to handle lots of requests because it doesn't actually do anything. It just has open I/O connections. Nope, you have a dedicated worker for just this particular process, and after that, it works on the next process. Which also means if you get another worker spawned and this panics for whatever reason, which means, I don't know, Stack Overflow, heap overflow, anything, any panic that can happen, it just kills the particular worker or the particular runtime within the worker, and then it bootstraps this worker again, and then you can run the next payload. So this is how AWS Lambda scales out various workloads across its system. With the typical consumption plan, you get about 1,000 workers that you can use. If you need more, either call AWS or the events are queuing up, which means that you need to wait for them. Does this answer your questions? Cool, great. I already said that if those processes hibernate for a certain amount of time, they are getting disposed and resources get freed. So this is how AWS Lambda works. One thing or a couple of things that are good to know, which were kind of interesting to me the longer I work with AWS Lambda, is that you are paying for RAM. So the amount of dollars that you are paying for scales within the amount of RAM that you use. So if you're using 128 megs of RAM, you have $0.000021 to pay. If you have twice as much RAM, you're going to pay twice as much dollars. But, and this is interesting, you're also getting twice as much CPU, which means that for most of the workloads that you're doing, it just costs the same. So if you don't have any workloads that need a particular amount of RAM that can work with a low amount of RAM, what happens is that if you get twice the amount of RAM, you get twice the amount of CPU. It costs twice as much, but it's also twice as fast, which means it levels again to the same amount. If speed is a problem with the application and not RAM, just go for the full gigabyte or for 10 gigabytes or whatever, it doesn't matter. It's the same amount of money that you're paying. Because if you have a smaller VM or smaller RAM, it just takes twice as long. And this is something that so I couldn't say that for any workload or for every workload that is happening, but that happens for a lot of programs that we have been running. So if RAM is not an issue, you can control the speed of the execution with that. All right, how are we going to write an AWS Lambda in Rust? Of course, we are bootstrapping a Firecracker VM, then we are running a Node process because AWS Lambda is Node everywhere, and Node is going to load a WASM file, a Rust program that is compiled in WASM, so it loads the WASM file and starts the WASM virtual machine. And no, please don't do that. Please don't do that. That's way too many virtual machines. That's way too many turtles. That's sadly what you see in the blog posts on the internet. So if you type in using Rust with AWS Lambda, you're getting stuff like that. Not cool. There's a more concrete way to do that, which is, well, just compile a binary and let it run on AWS Lambda. So you don't need to have any other abstraction, and it's actually quite easy. So AWS provides a crate with a predefined AWS Lambda runtime, which does exactly that. It grabs something from the queue. Then you can write your handler function. You can see that here. And once you're done, you send a JSON result back to the AWS Lambda queue. Hydro. So this bootstrap part that you can see in this async main function, so it's async, which means you need an async runtime. Tokyo would be my go-to runtime for that, and this is also one that AWS recommends. But this bootstrap code here can be always the same. The handler function is the actual function that you are going to implement. So this is the actual logic, the actual code that you are running. Then you compile it to unknown Linux GNU. The documentation says that you need to compile it to Moozle Linux. Doesn't matter, GNU works as well. It's just that with some glib versions you run into issues because the Amazon Linux version doesn't support a couple of symbols there. That's why they say in the documentation use Moozle, because it's the least painful Linux target to compile to. It's also the slowest one. So go for this target that works. You might need to install a linker if you are on macOS or something, but usually that works. I have even some GitHub actions that compile that stuff for you. I'm going to show to link to the repo where all that stuff is later on, so you can check it out. Name the binary bootstrap, that's the name. Put it in a zip file and upload it to Aws Lambda, and there you go. All right, let's look at some results. So, because Rust is really good at speed and memory. If I have a Lambda with 128 megabytes, and I run typical Hello World, which is just, okay, take the runtime from Lambda, the node runtime from Lambda, print out Hello World, and give the result back. A cold start takes about 200 milliseconds on a 128 megabyte Lambda VM. A rerun, so if the Lambda is hot, if the runtime is hot, takes about 2 milliseconds. In Rust, cold starts take less than 20 milliseconds. I couldn't tell if this is for the entire process that I have shown you, or just for the one particular piece that you have in control. Doesn't matter, this is what you're built for. So this is the number that counts. It's less than 20 milliseconds. So I had some cold starts in the ballpark of 60 milliseconds with the Hello World. That's great. And reruns usually are less than a millisecond, which is fun. So I had a couple of reruns where Lambda told me 0.5 milliseconds. Great. It also built me one millisecond because that's the smallest amount that Lambda can pay. All right. This is Hello World. This is not fun. This is not something that's in any way interesting. That's why I created a little benchmark program which is called Palindrome Products. What it does is that you take a range of numbers, let's say from 100 to 999. You create the combinations, like multiply 100 with 101, multiply 100 with 102, and do that with all possible combinations that they exist, and then see if the product is the same forwards and backwards. So 1001 would be a palindrome product because it reads the same from both sides. The nice thing about it is that this takes a lot of CPU if you're working with really big numbers, so you can benchmark really well how long this will take, because the bigger the range is, the more it takes. If I'm calculating palindrome products from 10 to 99, node takes for reruns, so I'm leaving out the whole cold starts because it's usually in the same ballpark as the Hello World. It's a very small program, so you don't have to do anything. Reruns are more interesting. And a rerun from 10 to 99 also takes 2 milliseconds, and of course in Rust it takes less than 1 millisecond. Surprise! Small numbers are fast, and surprise, Rust is fast. This is not something that you're interested in. What's more interesting is if you crank up the numbers, let's say from 100 to 999. 999 node takes about 500 milliseconds, and in Rust it just takes 45 milliseconds. So this is really, really fast. This is really, really nice. And if you're working with really big numbers, like calculated from 1000 to 9999, node takes about 70 seconds. And this is something where you hit a timeout very fast. You have to crank up those timeout numbers. Not so with Rust, because it takes about 8 seconds. So this is impressive. Of course, you can control it. Give it twice as much memory. CPU gets twice as much. Those times go down because it's twice as fast. But hey, same goes for the row down below. Same goes for Rust. But yeah, so those are the benefits of Rust in Lambda. First, one of the biggest benefits actually is that you have very, very small binaries instead of deploying the entirety of Node and your Node scripts and maybe a couple of Node modules or something. No, you don't have to deploy so much. You just have to run a 3 or 4 megabyte binary. This is, you can unzip it fast. You don't have any overhead in bootstrapping it. This is actually the biggest benefits. This is how you get those nice cold starts, because you don't have any overhead from anything else. And it works great on low vCPU. So if for the 128 megabyte VM, you're getting provisioned something between a 12th or a 13th of a vCPU, which is not that much. And Rust, since it's natively compiled, works also really well with this kind of CPU units. We have low RAM usage, so what we see is that in Rust you are just allocating the RAM that you use. Great. In Node, it always tries to be ahead as much as you allocate. So which means that if I don't know, I use 20 megs of RAM in Rust, Node allocates 40 megs of RAM. That's how the V8 works. But yeah. And also what I found out that you have less variation in execution. So if you're running benchmarks, which means I don't know, do 10,000 requests per second or something. See how Lambda behaves there. There are a couple of spikes where I don't know, you see that a VM is getting freed and or something queues or something like that, and then you can have spikes that even if your payload takes, I don't know, 45 milliseconds to run on Node, sometimes you have those 600 milliseconds or 1 second runs because Lambda can't handle it. If your execution times are very, very slow and very, very fast, Lambda is more able to handle that, so you have less variation in execution. And plus, it's super fun. So I love writing Rust, and writing serverless functions with Rust I love even more. Alrighty, cool. Let's go to the next provider, which is Azure Functions. And Azure Functions is very different in basically everything compared to AWS Lambda. So there are not that many overlaps, even if it looks like that. So when you're writing, I don't know, a Node application in AWS Lambda or Azure Functions, yeah, well, you're just writing this handler body and you're done with it. But there's so much nuance in basically everything that happens. So first of all, the triggers are part of the function definition. You define what your function needs to be triggered. You are defining the input and output binding. So you define the input, the trigger, and the sink, like the target, while you're writing the function. In AWS Lambda, you're just providing the function, then you configure the inputs. This might be the same in the end, okay, of course, but it also means that you can use the same Lambda for various input sources and output sources, not so much for Azure Functions. You have to define the trigger with the function. You can have multiple output targets, yes, but they are very much tied to what your function looks like. It builds up on Azure Web Jobs. If you ever run across Azure Web Jobs and oh, that sounds fun, it sounds also like serverless, that's what runs there underneath. The most important difference, I think, is that the unit of deployment is not just a single function, but an entire function app. So you're rolling out the function app and you can put as many functions in there as you like. Let's say you put 10 functions in there. That's great. The function app gets deployed and scaled out together, which means if Azure Functions requests another server, there comes the server, not a worker, a server, it bootstraps the entire app, all the functions that you have in there. If there's 10 functions, all the 10 functions are bootstrapped. This is a big, big difference. This also results in big cold start times, but it also results in very low cold start times for I don't know, all the other functions in your app, because the entire app is booted up. Also, those are then servers, which means they can take more than just one request at a time. You don't have them exclusively. So it might be just like with any other server, with a Node server or whatnot, that you need to process multiple requests in parallel. Alrighty, and it needs Azure Storage to store the function. So you can't deploy a function app without Azure Storage. Hidden costs. Just to see it. How does the Azure Function Execution lifecycle look like? So the scale controller checks if any events come in, and if those events come in and there's not a worker or a server already working on that, it allocates a new server. the server is unspecialized. So you can think of Azure having tons of Azure function servers in their cloud, but they're all unspecialized, which means there runs the function host, but the function host doesn't know what to do. The function host doesn't know which functions to run. It just is a dedicated function server. Once it's getting specialized, the files are mounted to the server. Virtual file system, so the Azure storage stuff from your Azure storage is mounted into this particular server. The app settings are applied, which means, telling which version to use of Azure Functions, what the runtime is, blah, 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 all the kind of things. Then the function host, and I'm sorry, this is very small, the function host resets the function runtime, reads the function JSON. Function JSON defines the input and output bindings. We are going to see an example later on. Loads any extension if necessary. Then the function runtime, and you're going to see that all in a second, loads the functions into memory, and then you execute the code. And you see there are lots of pink boxes, which means lots of stuff to do at cold start times. But you are also seeing that you have not so much to do when the container is already warm, when the server is already warm, because the scale controller says, is there an event? And the function server says, I'm going to execute it. So reruns are very, very fast. This is how an Azure function host works. So you get the trigger. The trigger is defined for the input binding. The Azure function host takes the input, and then it does either call an in-process task, which is written in C# or F#, because the Azure function host is written in C# on .NET. Also means that if you're writing functions in C# or F#, they're just getting linked together. I don't know if that's the correct word, because I haven't written any C# in over 15 years, but since it's the same technology, it just can run C# and F# stuff. If you're using something else that Azure provides for you, they have dedicated runtimes for that. You can see all those runtimes on GitHub. They are open source. And it calls this out-of-process runtime, which is either Node or Python or whatever, and it creates a gRPC connection with it. So it's sending events over gRPC to the function runtime. It processes those events in a gRPC-capable server and gives the results back. Third option, so those are not, they're not running in parallel, even though the image might suggest it. They're not running in parallel. It's an either-or. So you can either have in-process function apps or out-of-process function apps, or the third part, custom handler function apps, which means I give you an HTTP connection, do whatever you need to do. So this is where you can define whatever you like, be it a Deno process, like Deno is a Node.js similar language runtime for JavaScript, or Rust. So this is where we are going to implement our Rust Azure function runtime. The results are going to be sent back to the function host, and it sends it to whatever output binding that you need. Stuff that's good to know, RAM scales to your needs. This is very important. So in Aws Lambda, we are going to pre-provision a certain amount of RAM that you are paying for. In Azure function, it takes as much RAM as you need, not more, and you're paying for this amount of RAM that it takes. Also, the vCPU scales to your needs, up to one entire virtual CPU. Because Azure function hosts can do that. So it's not tied to the amount of RAM that you allocate or that you provision, just as much as you need. With the consumption-based plan, it scales up to one vCPU. If you have premium plans, you can have up to 4 or 5 or something. It's hidden in a number that's called Azure Computing Unit. And what I found out by Googling a lot is that 100 ACUs roughly are equivalent to one virtual CPU. Cold starts can be slow, but then again, since you have as much CPU as you need, those reruns can be very, very fast, and those initial runs can be very, very fast. And cold starts are for the entire function app. Alright, let's define the function host. So this is how it would look like if we are going to define a function host for a Rust application. There are two things that are important. So I'm not saying please do a Node.js application, please do a C# application, whatever. No, I'm saying I have a handler executable. So this is an actual executable like handler or handler.exe if you are on Windows, and enable forwarding HTTP request, which means that I want to communicate via HTTP with my application. This is a function binding. where I say, okay, for the endpoint palindromes, I'm talking here now about HTTP endpoints because it's the easiest to do. Please create this binding where I accept get and post requests as input, and I want to see a result on the output over HTTP. So those are the two bindings that you can do there. This is actually something that I really, really like in Azure Functions, because you can, for example, write services that send an email but also give a response back to the user that calls it. So if you have, I don't know, send email with a body or whatever, you do an HTTP request, it processes your request, and then you send it to two different targets, like an HTTP out, so that the user in the browser knows what to do, but you're also sending it to SendGrid, sending emails. Alrighty, and now Rust again. Hey, we are at the Rust meetup. The nice thing is any server will do. So if you're using Rocket, if you're using what I have here, Warp or whatever, doesn't matter if you have a server that a server framework in Rust, or you're writing your own server altogether, it will do. That's perfect. Any server runs. Funny, it's called serverless, but you are going to write the server because, you know, infrastructure serverless, not application serverless. Two things that are interesting. First of all, I need to have a path mapping that is equivalent to what Azure Function provides to me. So if I have, I don't know, a palindromes.js in Node.js that is mounted at /API/palindromes, in Rust, I need to provide that name in my app. So it's just forwarding HTTP requests, it's forwarding paths. What comes in my server is that this is a call to /API/palindromes, and please process this event. So you have to take care of that mapping, which is a little bit of extra work because you have to create those folders with the function JSONs, but you also have to create the same mapping again. There's room for failures, for errors that you are going to have, I don't know, a typo somewhere because it's all strings, you all know that. The other part that's actually quite interesting is that you listen to a particular function custom handler ports. This is a port that Azure Functions needs to spin up your server. This is an environment variable that gets forwarded to your application, and you listen to that port, which is also nice because if you want to try it out without Azure Functions, you just let it listen to any other port. So here 3000 in this example, I can develop the server in its entirety on its own, and then, yeah, those 3 lines, perfect, it runs on serverless, it runs on Azure Functions. This is sweet, chef's kiss. This is wonderful. All right, a couple of results. Cold starts in Node, Hello World, Azure Functions, around 700 milliseconds, give or take. Can be 500 milliseconds, can be 1.5 seconds. Usually it's about 700 milliseconds. Reruns though, 1 millisecond, because it's, again, then it's super, super fast. And this is now great. In Rust, those cold starts take less than 100 milliseconds. This is fantastic, because it's just so little to do for Azure Functions. I had cold starts in the ballpark between 30 milliseconds and 70 milliseconds, but 100 milliseconds is a good estimate, a good measure to say this is the cold start for my Rust application. Reruns less than 1 millisecond. Palindrome products, again, for very small numbers, already great. Node takes about 9 milliseconds. Rust takes less than 5 milliseconds. The bigger the numbers get, I have about 80 milliseconds for Node. This was 500 milliseconds with the small AWS Lambda VM, and I have about 50 milliseconds in Rust. This was 45 milliseconds in AWS Lambda. The great thing is, if you have big numbers, it takes in Node about 10 seconds, and in Rust less than 1 second. So this is fantastic because, you know, CPU scales with it. But what you can see here, as well as with AWS Lambda, if you are doing stuff in Node or in Rust, factor of 10 is a good estimate. So 10x fast. What benefits do you have of Rust in Azure Functions? And we have a little lag here. All right. First of all, significantly lower cold starts. Cold starts was always a very big problem in Azure Functions, and they did a huge amount of effort to get that right. So I can remember presentations where I showed Azure Functions, and it took me 1 to 2 minutes to have a cold start of a Node.js application. Now with 700 milliseconds, it's really, really great, especially since reruns are so fast. But you can cut those cold starts down tremendously if you're doing Rust. What I found great, it's just a server. So any server will do. It doesn't matter which server that you use, even servers that you already have. They are immediately serverless, infrastructure serverless, because you just tell them this port, this path, and you are done. just configuration for you and it runs in a serverless offering. You're just paying for what you need. That's great. Cold starts in Node.js or other runtime environments depend a lot on the amount of functions that you have, because all of them need to be compiled on cold start, not a problem with Rust. So this is also something to keep in mind. And again, it's a huge amount of fun. So I love writing Rust, and it's equally fun with Azure Functions. And this is actually my preferred way of doing servers right now. Just having Azure Functions killing out my Rust servers, because hey, it just works. Alrighty, that's for the stats, that's for the milliseconds, that's for my tests. Summary. First of all, Rust should definitely be considered if you want to write serverless functions. It's a great tool if you like writing Rust. For some cases, you can benefit a lot, especially if you have processes that maybe need to run in the background, that are CPU heavy, that really need to compute something. This might be your number one choice, because it works great on low vCPU, it's fast, it needs just a little amount of memory. Rust in all cases can help significantly with cold start times. So if cold starts are your problem, Rust might be the choice for you. Execution times, I focused a lot on execution times. Keep in mind, we are not talking about hidden costs. We're not talking about Azure storage costs. We are not talking about AWS API gateway costs, because this is, you get the HTTP bindings in AWS Lambda for free, big quotes. Sorry, in Azure Functions for free. But in AWS Lambda, you have to activate the AWS API gateway, and there you're paying per traffic again. So it's calculating the entire thing is a nightmare. Seriously. I couldn't give you an estimate which one is cheaper. I honestly don't know. They're just too different, and I'm just running in free plans since the beginning, so I can't tell you which one is more expensive depending on the factor that you have. Doesn't matter, both get cheaper with Rust. So those are the benefits of Rust. If you want to read up on that, first of all, if you read up on Azure Functions, I can highly recommend the entirety of the Azure Functions documentation on what is the docs.microsoft.com. They're excellently written. It's amazing how much information you get about everything in there. And if you don't find the information in the Azure Function docs, you find it on GitHub, because most of the things are open source. So you can read up on the entire Azure Function hosts, how it works, on all the runtimes, how they work, and also lots of examples for other programming languages. So if Go is your thing, do it in Go. You have a tutorial for that. So this is great. One of my colleagues at Dynatrace has written a blog about what happens behind the scenes when AWS Lambda call starts. This is where I grabbed all the graphics from. It's a great read, check it out. And also check out the blog from AWS Lambda on the Rust runtime for AWS Lambda. This is where you're going to see a nice Half-Life logo, but also some great content for the AWS Lambda runtime. Last but not least, this GitHub link has all the examples from today, so you can check them out, like literally check them out, like Git check them out, and try them. And that's about it. Thank you very much. 40 minutes. Great. Cool. Alrighty. Do we have any questions? Yes.
Actually, the questions first about cost. So even if you go on a free plan, they provide you some estimations for costs and what is your impression, what is cheaper.
But it's so hard to tell. So the repeat the question for the folks on YouTube. Even if I'm in free plan, there are some estimates out there, and if I could tell which one is cheaper given those estimates. And the cool thing is that usually AWS Lambda gives a number like $0.00021 per millisecond, and a couple of months later you see a similar number on Azure Functions, which is usually, I don't know if it's 0.00021 in Lambda, it's 0.0000 whatever 17 on Azure Functions, and given from that you could say, okay, Azure could be cheaper. But then again, cold start can take longer. But then again, reruns get faster. So it honestly depends on the on the load that you put up on your servers. This is when I know how much load your servers get, or which load do you expect, the number of requests that you expect, the number of workloads that you expect, and if you have a rough estimate of how long they take, then you can do really good estimates. One thing that we found out, so again we have spent a lot of time with Aws Lambda. One thing that we found is if we have our servers on constant load, like an EC2 server that we are providing on constant load, and try to give the same load to Aws Lambda, it levels out. So those numbers are not just we make everything cheaper, everything more expensive. If you have the same maximum load that you would expect from an EC2 instance and from Aws Lambda, it usually levels out to the same amount of cost. Where you save money is if you don't need to run the same amount of load the entire time. This is where you actually save money. And I figure with Azure Functions it's the same. Azure Functions can get very expensive if you're going into premium plans, because it says premium, and that's totally okay. Premium gives you a lot of benefits, much more CPU, much less high cold start times, so lower cold start times. So if you're an enterprise and you need also features like put it in your virtual network and stuff like that, the premium plan from Azure Functions are great, but they're also more expensive. But yeah, so then again, I haven't paid more than $3 per month for Azure Functions. There's a nice article out there from Troy Hunt, who transferred his entire Have I Been Pwned app, you know, the one thing that tells you if your email has been compromised, where he reduced cost to $20 a month just by moving to Azure Functions. So that's a great read. Okay.
And the second
question, yeah.
So it's not about AWS Lambda or Azure Functions, but it's kind of related to Rust and function as a service. A couple of years ago, I read like Rust goes very like hand to hand with WebAssembly, and there is a company, Fastly, that has an idea of edge computing. So they have an idea to run this WebAssembly code on the edge servers. I tried to find something like how to do, but I did not.
Very good question. So the question was, speaking of serverless workloads, Fastly is constantly talking about WASM on the edge, like WebAssembly on the edge, and Rust compiles to WASM. Yes, absolutely, this is the future. Check out Crustlet. Crustlet is a Kubernetes Cubelet that runs WASM workloads in Kubernetes, which is exactly this idea of not compiling something into a guest operating system like Amazon Linux or whatnot, but rather having lots of WASM VMs running WASM workloads in them. Absolutely. That's.
To spawn Crustlet, do you need to spawn your special Kubernetes, so you can use like any Kubernetes environment from AWS, Google, Azure?
Yes, you can run them on EKS, AKS, whatever. Absolutely. You had a question?
Do you have tested where you can execute more requests per second on a high load?
If I have tested where we can run more requests per second on a high load, no, no and yes. So yes, we have tested Aws Lambda and Azure Functions both on high load. So as we speak, my colleague is doing a lot of load tests on Aws Lambda. Hello, Philip, if you're watching. A great load testing script. We haven't found the number yet where we can feel the load. So this is very reassuring, to be honest. So you know, even if the Azure Functions server is under high load, Azure Functions spawns up another server. Great. And this scale out seems to work really, really well.
Can you see steps when they scale out?
If I can see steps, yeah, I can see spikes when one thing that should be a warm start is actually a cold start in disguise. Yeah, that's something that you can see. Rainer, do we have questions from the chat as well?
I will check.
Yeah. Any questions from the audience? From the audience. It's great having an audience. Yeah.
What of those environments do you prefer when it comes to testing or to developing on a local machine, or is this even possible? And how does
which environments do I prefer when testing on a local machine? So, testing on a local machine is great for both. Azure Functions has an entire CLI where you can start an actual function host on your operating system, and everything works just like it would work on Azure Functions, which is a lifesaver at times because the apps are actually like they are on your machine. And AWS has the serverless application model, which basically does the same. But it's one thing that I don't like about SAM, that it's another flavor of AWS Lambda, where you could theoretically work without it. You also have the serverless framework. The serverless framework is a great way to start developing serverless applications, no matter which cloud provider that you are choosing. So if you decide for AWS Lambda or Azure Functions, the serverless framework has templates for both environments and lots of tutorials. Like their GitHub repo with examples is full of examples for OpenWhisk, OpenFast, Knative, KEDA, Azure Functions, Google Cloud Functions, AWS Lambda, all of them. And we have tried them all, and they're all not good except Azure Functions and AWS Lambda, to be honest. But yeah.
Here's the question from the audience.
Can you also use Windows Cubelet for Azure Functions? Is it only limited to Linux? So Azure Functions runs either on Windows or on Linux. But if you have a custom handler, it has to run on Linux. So you can't compile a custom handler on Windows and ship that to Azure Functions. This is one of the restrictions that I found out here. Or maybe I just couldn't because I have a Mac and I can't compile to Windows executables. And it needs some effort to compile to Linux, but on the other hand, now I do it with GitHub Actions, so it's great. Righty. So many questions, that's great. Do we have something more? Alrighty.
We are fine from the audience.
Cool.
Yeah.
Yeah.
Would you expect to have if your Azure Functions basically runs C# or is already C# and can directly, would you expect that C# is even faster in Rust than your example for Azure Functions?
Yeah, the question was if since the Azure Function host is written in C#, wouldn't the C# function be faster because you overcome the entire thing of bootstrapping an external runtime? I honestly couldn't tell. And I'm very sorry for that. I'm especially sorry given that I know there's so many .NET developers here in the audience today. I haven't written any C# and I have so the last time I've written .NET was .NET 1.1. That's pretty old. And that wasn't very fast, but I guess they did the homework as well. So one thing that I have to say for that, there is this thing called Azure Durable Functions, which is an orchestration layer on top of Azure Functions where you can preserve some state between those stateless or quote-unquote stateless serverless function that you write in whatever language that you like. And you can't write durable functions with a custom handler. You have to use a predefined handler because there's a whole SDK attached to it. And this I would do, I guess if speed is an issue, I would do that in C#. Because C# is definitely faster than Node.js on Azure Functions, yeah. But I couldn't give you any numbers, I'm very sorry. Alrighty.
I would like to share a video.
Yes.
Maybe you can announce that. I would like to show people how it currently looks like. Here
So Rainer wants to share a video, folks. So you can't see the video. I'm so sorry, folks in the audience. But you know how it works. So folks in the internet, this is where we are right now. And this is alright. If there are not any more questions, shall we do Shall we do a break?
Yes, we will do a break
Yes.
now, and it's announced. Maybe you can repeat what I say, or you give me quickly the microphone so that everybody hears it.
Sorry, folks from the internet. Now I'm even more sorry. There you go.
Awesome, thank you. Okay, now we will do a short break. It is announced that my talk will start at 8 p.m., so we have approximately 25 minutes, and that means for all who are here, cake time. We will now go for the cake. We will now anschneiden. I don't know the English word for that. Break the cake into pieces and enjoy a sweet Ferris. And we will be back with content at 8 p.m. And then you will hear the second talk of today, my talk about traits, which are not your grandparents' interfaces. Stay tuned, come back, enjoy the cake. We will see you at 8 p.m. Na, wie schaut's denn jetzt aus? Ui, 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 ui. Zweiter Versuch, Stefan. Ich glaube, jetzt müssen wir das Issue weghaben. Wie ist?
Passt gut.
Does it work? So let's switch to English. Okay, ladies and gentlemen, grab your pieces of cake, whatever you want to have for the next few minutes. Grab a drink and take your seat because we are going to start momentarily in a minute or so with our second talk of the day, which is Traits Not Your Grandparents' Interfaces. And for those in the online audience, please stay with us for another 1 or 2 minutes and then we are going to get started. If you have any questions during my talk, please write them. The best way to ask them is to write them into the YouTube chat because I have the YouTube chat right here beside me. I can see your questions and I can try to answer them. Stefan, I think, will also monitor the Discord server and will relay any questions that you ask there. Okay, so I think we are all here. If you have any audio or video problems on the internet, please let us know and I will do my very best to fix them as quickly as possible. Good. Stefan, what do you think? Should we start? Should we get started? Yeah, we should. Okay, hello and welcome to the second talk of the RUST LINZ meetup. We are really enjoying ourselves here at the sun deck of the Grand Garage, and in the pause I already shared a short video, a drone video, which our friend Raphael has shot, and we will share more videos about how it is here in Linz live being at the meetup. I hope the summer will be long and we will be able to do more in-person meetups here at the sun deck of the Grand Garage. But now let's get into our second talk. Let me quickly introduce myself before I go right into the topic. So let me switch it up here, and now it is like it should be. Okay. I think a good idea is to introduce oneself. Let me quickly introduce myself to you. My name is Rainer Stefan. Together with Stefan, I founded the RUST LINZ meetup. Personally, I am a passionate software developer. I have been writing code for more than 25 years, and I always say every day where I can write code is a good day. Unfortunately, I can't write code every single day because if you work in IT for a few years, you have some management to do, you have some project management to do, you have to do some sales stuff and so on. But many days are, for my personal life, are coding days, and I really enjoy that for more than 25 years. I'm a Microsoft MVP and regional director. That does not mean that I'm on the payroll of Microsoft, not at all. That means that I do just a lot of work with the community, and if you do that, you are promoted to a most valuable professional or a regional director. That's all. So, to make a long story short, beside my professional work, I do a lot of trainings. I am a part-time teacher. I'm a mentor in the community. I'm chairman of the coding club Linz. We run the local Codedojo Linz, which is the programming club for kids here in Linz, and of course the RUST LINZ meetup. That's essentially me, and if you would like to get in touch with me, on the right bottom side of the slide you see my digital business card. Just click on the link or type it in, it's not that complicated, and on the right lower bottom you find links to LinkedIn, Twitter, Facebook, my YouTube channel, and so on and so on. So I invite you to get in touch with me. Enough introduction. Let's take a look what we are going to do. We are going to play tic-tac-toe. I said I love writing code, and I learn most when I write code. And one of the traditional things that you build in a new language is a tic-tac-toe game, and today we are going to build tic-tac-toe. Well, it will be more of a code walkthrough because so many things are here live, here outdoor, and so on. So I wasn't I wasn't brave enough to type the code live, so it will be a code walkthrough, and I will show you my points with existing code. And of course, I will over-engineer the tic-tac-toe game a little bit, because then with an over-engineered tic-tac-toe game, you can learn a lot. On the way of building this tic-tac-toe game, we will learn some things about traits. If you want to take a look at my code in detail, I cannot talk about every single line in just an hour. You can use this link that you find here in my slides, and you can click on it, go to GitHub, and take a look at it. By the way, I maybe should quickly share the link of my slides. Let me do that. Let me quickly go to slides.com here and have, where is this one, and let's share this one. This is the link, you see? This is the link, and can I quickly copy that into the chat? I think so. I think I can do that live. And here is the link. It's in the YouTube chat now. So if you would like to follow the slides directly online, you can now take a look at the YouTube chat, and there you find the link to my slides. Good. Without any further ado, I would say, let's get going. Thank you, Stefan. Please, go to, yes, next slide. Okay, internet is a little bit slow here, so you don't see this funny GIF here. That's one of my favorite games when I was, too fast. Don't do the spoilers here. Just one. This is has been one of my favorite games when I was a kid. Anybody know this game? Yeah. Prince of Persia is exactly, and you see this one is really the basic stuff. We are just entering the first level. We are opening a first door, and that is a good thing to get started to talk a little bit about traits. Okay? What is a trait? Let me quickly copy this one to show it to you live. This is a very, very simple example, and in order for you to follow along more easily, I will go to the Rust playground. Give me the Rust playground here. Come on. Here it is. And let me copy in these few lines of code that I have here and zoom in a little bit. You know, when I first played with Rust and I read about traits, then I viewed traits from the viewpoint of a C# TypeScript developer kind. Because I write most of my days C# code, TypeScript code, sometimes a little bit of Go code, but to be honest, I viewed it from the viewpoint of a C# developer. And when I found something like this, as you can see it here, pop, trait, computer, get answer, self, whatever that self is, self sounds like this, and this arrow with U8 means we are returning probably a byte, something like this. This looks very much like an interface. I know that. In C#, I would build a struct or a class. I would create an interface, something like this. This could be a struct. You could ask yourself, why a struct without members? Yes, that's possible. That's definitely possible in Rust. That is called a unit struct. And then you can implement, as you can see it here, you can implement a trait for a certain struct. It looks a little bit different than in TypeScript or in C#. It looks pretty similar, kind of with Go, but it feels like an interface. It sounds like an interface. It smells like an interface. I think I understood that. That is fine. And as you can see it here, I can instantiate deep thought, and I can ask deep thought for the ultimate answer, and probably if I run this, I will get 42, of course. That's a very simple getting started. That was my first introduction to traits. But when I got more interested in the details, and let me try if I can zoom in a little bit, I was asking myself, okay, what happens behind the scenes? And if we take a look at the generated assembler code, and I have copied it out here, I used the Rust playground to generate the assembler code. What I essentially saw is that this interface was nearly gone. It's not visible. Well, it is kind of visible a little bit, only in the names of the generated jump labels here, but essentially it is gone. If we call this method getAnswer, which is a method from a trait, then we essentially get a call assembler statement, directly a call assembler statement with the static dispatch of this method. Really, really simple. So I think this is what many Rust developers means when they say zero trust abstractions, zero cost abstractions. I'm very sorry. They are trusted. Okay, not a good phrase here. This is what you can call a zero cost abstraction. You can build interfaces and you don't pay for them at runtime. That's a very good news. Okay, now let's go into our tic-tac-toe game and take a look at basics applied to the tic-tac-toe game, and then we work our way through to more complicated stuff, because this talk is called Traits Are Not Your Grandparents' Interfaces, so obviously there has to be more about these traits. Let's take a look at one of my first things that I implemented here. Let me quickly look for the code that I would like to show you. Where is it? Where is it? I'm going to find it, and it's here. Let me zoom in a little bit so you see it pretty good, close. Here you see a trait. And in this case, for demo purposes, I created a structure which is called board content. It will hold the data for my tic-tac-toe game, okay? It contains essentially a 3x3, so 9 elements of size U8 array. So 9 bytes for 3x3 elements for our tic-tac-toe game. And in this case, I wanted to build an abstraction which I called toCompactString, which does nothing else than taking all these 9 elements and turning them into a string. Very, very obvious code. Even if you have not written a lot of Rust before, you will probably be able to understand this code from the context. There is a lot going on here with traits, but we will discover that a little bit later. For now, you see the board content, which is my struct. Here you see the struct, and you see the toCompactString, which is a trait, and I implement this trait for my board content. Okay? That should be pretty obvious. Any questions to this code? Maybe those of you who have not written a lot of Rust code, I know there are some people here in the audience who have not written Rust code. Some of the beautiful things. Do you see the missing return statement? Yes, I don't need a return statement. You see, I just write result without the semicolon at the end, and that's the return. You know what? Since I mix Rust and C#, I think people think I'm stupid whenever I give C# talks, because I always forget the return statement. I call myself a C# trainer, and I don't know how to write the return statement. So if you see that, if you see me doing that on stage, now you know why I do that. Because maybe in the morning I wrote Rust, in the afternoon I write C#, and I always mix it up. So this is Rust, this is interface, this is traits, and this is the first step. Let's go back to the slides, and let's take a look at my second node. Yes. Let's take a look at a little bit more advanced example. Let's fold that one, and let's take a look at this one. Let's make the font a little bit larger so everybody can see it properly. Here you see this one, a square content. It's an enum. Many of you know enums from many different languages, and Rust has enums too. This is a so-called fieldless enum. That means we don't have any additional data, because in Rust we could give additional fields to certain elements of the enum if we want to. So we could say, well, in the case of an X, I want to have additional data like A8 or a whole struct or whatever. You could add additional data, but I'm not doing that. The first thing that you have to see and recognize here, and that is pretty awesome, see that one? We can implement traits. In this case, this is a system trait, the default trait. That allows Rust to understand what the default value of a type is. I didn't define this trait. This trait is system defined, but I can define traits on enums. That's pretty awesome. In many other languages, you can't do that. Additionally, you might recognize that up here, I have this strange thing, hash derive, with debug and copy and clone and partial equal and equal. Guess what? All these things, debug, copy, clone, and so on, are traits. And what you see here in line 4 is the so-called auto-implementing. We can just ask Rust to auto-implement all these interfaces for us. This is a macro, so Rust comes with macros, and these macros can auto-implement traits for us if they are pretty simple. For instance, there is a trait here, copy, which just says I can copy this data type by copying the underlying bits. This can be auto-generated. There is no reason why I have to write code for that. And this is the derive macro that you see here. By the way, if you want to know what's going on behind the scenes, you can always copy this stuff, go back to our good friend, the Rust playground, paste it in, and then somewhere, I think it is here, yes, expand macros, takes a second, and here we are. See, this is the code that is generated. No, I will not walk you through this code. You can do that experiment on your own, but that's essentially what's going on behind the scenes. Auto-generating traits for your data types whenever they are pretty simple and when they can be auto-generated. That's going on in the first few lines of code here. So you see, a little bit more than just interfaces, isn't it? Let's go further. The next thing here is another system trait that I implement here. You see, square content is again our enum, and this time I'm implementing the from trait. From is typecasting. If we want to have typecasting, we implement the from trait. So in this case, I'm saying I want to be able to generate a square content from an unsigned byte, from 8 bits. And then I use the match statement of Rust in order to turn the values of the unsigned 8 into square content fields. If the value is not available, then we just panic. Oh my God, I cannot convert that one. Okay? The beautiful thing here is that there is a second trait, which is called into. It works exactly the other way around. So what you can say, you could say implement into for U8 for an 8-bit unsigned 8-bit unsigned byte to turn it into a square content. So we have from in one direction and into in the other direction. So which one should you implement? And now comes the beautiful thing, something again new for those of you who haven't looked so deeply into Rust. You get it for free. If you implement from, you get into in the other direction automatically without writing a single line of code. If you are not an experienced Rust developer, you can now ask yourself, how could that be? How is that implemented? Is that magic built into the Rust compiler? No, it isn't. I will show you the source code in the Rust library in a few minutes, where you will see how this magic is done, how this works. And guess what? The magic is traits. Again, traits. Okay, here you see, yeah, question.
Does it work only if you implement from? If you implement into, will it?
Oh, very good question. I will repeat this question. Could I implement into and get from for free? Yes, you would do that. But it is recommended that you always implement from and not into. That's a kind of that's a kind of convention if you want. Stefan.
Into is implemented in the standard library.
Yes, into is also.
For all,
yeah.
Everything that implements from gets an into.
Exactly. That is what I meant with you get it for free.
Yeah, I
yes.
don't think it's vice versa. I haven't seen the from trait implemented.
I'm pretty sure.
Okay.
I'm pretty sure. I'm not 100% sure, but I think I have to check it. It's a good thing. I have to check it. But if you implement from what I said, you get definitely into. Okay? And just implement from, that's the convention. Thank you, Stefan, for pointing that out. If I'm wrong, I'm very sorry for that. I always implement from, so maybe I forgot something. You see, I wrote some type conversions, and let me quickly go down here. For those of you who have not written so many lines of Rust code, these are unit tests. You see, line 63, 64, these are unit tests for the code that you have seen above. And now we can take a look at how these traits are applied. You see, for instance, take a look at this line of code here, this one, line 71. Here, I'm saying default. Default is the name of the trait. I can call here the method default, and Rust is smart enough to recognize that on the left-hand side of this assert statement, I have a square content, and it automatically knows that it has to call the default implementation of square content in order to be able to compare both sides of the equation. Understood? Yeah? For the C# developers here in the room, that would be the default keyword in C#. That would essentially do the same. But here, even that functionality is based on traits, the default trait. Here you see the from and the into part. Let me quickly draw a little bit here. Here you see the from code where I convert a 1 byte into the square content. And again, Rust is pretty smart, even with the traits. If I hover over the 1 here, it recognizes automatically that this has to be an U8, because the from trait into the square content is implemented only for U8. So therefore, I don't need to specify that this is a byte value. I could do that, but I don't need to. Let me quickly show you that. Come on, internet, wake up. Hello. There is a short internet glitch here. I hate that when that happens. Yes, my Wi-Fi is suddenly gone. Luckily, we are projecting from a different computer, which still has Wi-Fi. So let me quickly switch to our second Wi-Fi. I hope it will work. We have 3 Wi-Fis here, just to make sure. Okay, so let's see. And it looks good. Here we are again. Very good. We are online again. Stefan, it was a good idea to bring so many Wi-Fis with us. This is what I meant. You see it? Oh, it's a little bit slower here. It's fine. Here you see, this is what I meant. I don't need to add U8. Rust is analyzing the traits automatically, and it finds out that this U8 is not necessary because it understands that the from trait is available for U8 into square content, and it does all the magic automatically. Okay? And here you see that it works vice versa too. 1.into, I get it for free. 1.into calls the from trait, but the from trait is implemented in the other direction, so it works pretty well. Raphael, you have a question. You want to know what happens if I, for instance, say something like I32, something like this. Then we will get an error because, let me hover over it, there you see that there is no from I32 trait, so therefore Rust cannot fulfill this magic. No, in Rust, type conversions are always explicit. You don't get implicit type conversion if the compiler cannot be absolutely sure. If it is absolutely sure, then you get it. Otherwise, you have to explicitly write typecasting. Thank you for this question, Raphael. So this is the into part. Next one is string. I did the same for a character, as you can see it here. And just to add a little bit of extra for those people here in the audience who have not written so much Rust code, this is how you would write a unit test which is expected to panic. It has nothing to do with the trait, but I decided to just let it in here so you see it and maybe it's interesting for you. I see some people nodding their heads. I know you are C# guys and TypeScript guys and so on, so you have probably seen a little bit of Rust but not so much, so this is how it looks like. So this was, again, a little bit of basics, and with that I go back to my slide deck. This is the wrong one. This is the right one. Here we are. We saw from, into, default, everything's fine. Now let's go one step further and take a look at the board index class that I created. Not class, of course, a struct, because we are talking about Rust here. What is the board index? The board index is a struct, here you see it, which contains, behind the scenes, just a usize value. A usize value is just an indexer in an array, and the size depends on the machine's register sizes. In my case, it's a 64-bit machine, so it's a 64-bit value that you see here. That's usize, essentially. And what I want to build is I want to build a secure way of indexing in our 3x3 board. So I want to build an abstraction on top of usize that can only contain valid values between 0 and 8, nothing else. And then I would like to build an indexer logic in our board where I can specify indexing, a custom indexer with our own type. Okay, so let's take a look at that one. Here you see, this is our board index type. The implementation is not that interesting because we want to focus on traits, okay? The implementation of board index is not so relevant for traits, so I will quickly go through that and go down, down, down here where we start to see again some of the traits. The first traits are pretty obvious because you already learned about them. I built a type converter from usize to the board index. Okay? Sorry, the other way around. This is what, sorry, I was confused. This time I'm implementing an interface on a standard type usize to be able to convert usize, sorry, the board index into usize. Now I have it correctly. Sorry, I was a little bit confused. So I'm telling the system, whenever you have a board index, I'm clicking too much, and it's too slow here, so here we are. Whenever you have a board index and you need to have a usize, you can directly take the inner value of the board index and return it. So this is another takeaway that you can get from this talk. You can easily implement traits on top of system data types. In this case, I'm implementing a trait for usize, a type which I definitely did not implement on my own. I can also add it to a string, which is a Rust string. This is not a string that I invented. I'm allowing here to turn a board index into a string by just formatting it as a number, nothing special here. The other way around is just calling a method. This method checks whether the value is between 0 and 8, that's fine. And I also do some parsing. How does parsing work? ix is a string. And now suddenly Rust knows that parse has to parse a value and turn it into a board index. How does it know that I invented the logic that a board index is represented by a string combination like A1 or A3 or C2? How can parse know what to do? Now, what is the talk about? Traits. Therefore, it knows it because we have a trait. There is a system trait which is called fromString, and fromString essentially powers parsing. So if you implement the fromString trait for a data type, in this case a static string, I just implemented here for a static string, and then I can write some parsing logic. And here you see, I will not go into the details because this is just Rust, and if you're not familiar with Rust, you can take a look at the code afterwards. The essential thing that I want to tell you here is that this again is a trait, and by implementing this system trait, I get the parse statement for free. It knows that it has to call the fromString trait, in this case the fromString implementation, so to turn everything into a valid board index. Some of you might have a little bit of problems here because you might ask yourself here, what is this result all about? That's essentially a data type in Rust where I can specify that the result can be either self, in this case the board index, so I successfully created a board index from the string, or I create an error type. Result is an enum, and this enum has two possible values, OK and error. OK would be that one, and if I scroll down a little bit, you see this is the happy case, and this is the second one, this is the error case. This is where you have something like this. So this is how the fromString, the fromStir trait works. You just return either the OK happy path or the error, depending whether you could parse the value. And everything is built on top of this trait. Let me quickly take a sip here and wait whether we have some questions. Matthias asks, any reasons why you didn't use rustdoc 3/? Here in this case, it's not really, Matthias, it's not really a documentation for this trait. It's just notes for me to remember what I want to tell you. So Matthias is perfectly right. Rustdoc, the correct way of writing documentation in Rust is with 3/ and not 2/, but these are just my personal notes, not documentation. We have a video, I think, Stefan, in our library where we had a full hour talk about how to create awesome Rust documentation. So if you are now confused by me doing it not right, take a look at this video. This video is awesome. You will really learn a lot in this video. Check out Rust Linz AT, you will find it there. But thank you, Matthias, for pointing that out. Let's scroll down a little bit. And we have a new trait. Of course, traits, the display trait. What is the display trait all about? The display trait is the trait that is used by the print line macro or the format macro. Let me quickly scroll down a little bit and let me take a look. Do I have a unit test for that? Yes, I have a unit test for that. You see, this is the using of the display trait. Whenever you use the print line macro or the format macro to turn a board index into a string, and you use this curly braces open and close thing here, Rust knows that it has to call the display trait in order to turn the board index into a proper string. In our case, A1, B2, C3, something like this. There is another trait which is important in that regards. It's the debug trait. You can auto-implement it, or you can implement it by hand, and this is used whenever you use the colon question mark syntax to print the debug output of your value. Okay, that is a different trait. But in this case, we are talking about the display trait. This is another important one that we have in this example. Display trait. Last but not least, we have two interesting ones. Add and sub. Again, two system traits, and these system traits power what? What do you think? Plus and minus. They are powering operator overloading. So you have to implement a trait, and in order to be able to use the plus and minus operator. So in this case, I'm implementing add and sub on the board index so that I can add and subtract board indexes from each other. Let me scroll down a little bit and see whether I can find the prop. Yeah, here you have it. You see? Here in this case, I am taking a board index and I'm adding let's hover over it, usize on top of it, and the result will be another board index. And here I can subtract something from my board index in order to reduce my board index, and the result is again another board index. So if you want to have operator overloading in Rust, implement system traits, and then you get support for the plus and minus operator out of the box. So you can already see that traits are very, very deep into the ecosystem of Rust. Whenever you write Rust code, you have to deal a lot with traits. Other languages, like C#, a language that I know for more than 20 years, I think, they are doing it completely different. They are having, for instance, static members on types where you can do operator overloading, completely different like Rust does it here. By the way, if you ask yourself, hey Rainer, what is this stuff? This has nothing to do with traits. This is a very interesting crate. It's a kind of library which is called RS test. RS is not my name, it's not Rainer Stropek. I have not written it, somebody else has written it. And it's essentially data-driven unit testing. You can easily write data-driven tests like this in Rust. It works like a charm. I really like to use it. And I think even those of you who have not written so much lines of code in Rust, you will be able to guess from the context what this stuff is all about. Nice. So let's go back to our slides and let me check. Yeah, I promised you that we will take a look into why we get this into for free if we implement from. And what I did is I looked up the relevant code piece in the Rust library in GitHub. And here you see what the magic does. Take a look at that one. And that is pretty awesome and pretty different to many other languages. Latest here, at that point in time, you should understand that traits are way more than the usual interfaces you might know from other languages. Take a look at this type. This is an implementation of the into trait for any type T, line 45 here, for any type U, where U implements from. So essentially, into is auto-implemented for any type offering from by just calling from in the other direction. So you can implement traits on top of other traits. You don't need a concrete data type. Trait in German means Fähigkeit. So you can derive a trait from another trait. Let me say one German sentence here so that it's very clear for the audience. Eine Fähigkeit auf Basis einer anderen Fähigkeit ableiten. This is what you essentially do here. And by having this line of code here, we get into for free when we implement from. Pretty nice, isn't it? Okay, very good. Back to the slides. Did I forget anything? No. Let's continue. Board content. I showed you that we have a trait there which is called toCompactString. Let me go back to the board content. Here it is. I implemented toCompactString and I implemented it on top of board content. But I asked myself, what can I show you more? How can I show you what we are capable of doing in terms of doing more powerful abstractions? And here I have added a second trait, board iter toCompactString, which is very similar to the toCompactString trait, but this time it's the same signation, you see it? I can copy it I can turn it into a compact string representation, but this time I'm implementing it on top of, you see it here, an iterator over an array. So I'm no longer implementing the trait for a concrete type like the board content struct, but I know that my board content internally has a static sized array, 9 elements. Therefore, it is very simple to implement an iterator. Essentially, the array already implements an iterator. And if I have an iterator, I can abstract my trait, board iter toCompactString, away from the board content and build it on top of the iterator over the array. And therefore, my trait implementation is now more flexible. It works with any iterator over any 9-element array here. It doesn't need to be my board content. It can be your board content, as long as you can provide a static iterator iterator over an array, you're fine. My implementation will work for you. So this is the application of this building a trait on top of a trait, now not in the standard library, but in my own application. I can make my implementations more flexible. I can make it more widely usable. That's the idea here. It's just a demo, so don't ask for the why is this really a good idea? Is this the best design? Probably not. But I want to showcase some of the features, what you can do with traits. Okay? That's my point here. So let me take a sip of water here and wait for any possible questions. Okay, good. No questions currently, so I think you want to know more. Good. I just opened Pandora's box of the iterators. No, it's not Pandora's box. It's a huge cake, a huge playground. Iterators are awesome in Rust. I come from the world of, I mentioned that before, C#. And in C# we have an awesome functionality which is called LINQ. I love it. Language integrated query. It's so awesome. MapReduce if you are a JavaScript developer. And in Rust it's iterators. On top of iterators you can do all the crazy stuff like mapping and filtering and summing, and all this stuff is built on top of iterators. So let me quickly show you how we can turn our board content into an iterator. That's pretty simple. We can, for instance, implement the trait into iterator for our board content, and then this into iterator trait has something unique, which is again very special for Rust, and I don't know this feature from other interfaces, from other implementations of interfaces in other languages. In this case we have, let me draw a little bit here, we have parameters for traits. So the into iterator trait demands 2 parameters. You have to tell it, okay, what is the type that we will get back item by item? And secondly, you need to specify a structure that you will use as your iterator, because the iterator is represented by a structure, by a data type. If you create an iterator, you are essentially creating an instance of a struct. and you can choose this struct. You can choose which struct you want to use. In this case, I'm just using the existing struct of the underlying array. So I'm using the array into iter, and I'm just asking my internal array for its iterator, and I'm just returning it. And with that, I offer the array iterator on top of my board content. In a second, you will see that we can build completely custom iterators with complete custom iterator types. You will see that in a second. But in this case, I'm just saying I am hiding the implementation from outside, but I'm passing on the existing iterator logic by using the existing array iterator and just returning it here by implementing this into iterate. And when I have that one, I can, for instance, use a loop statement to iterate over my board content. Understood? Okay.
Sounds like Haskell.
Sounds like what?
Haskell.
Sounds like Haskell was the comment. I have no idea because I've never written a single line of Haskell. I believe you. I absolutely believe you. Let me show you what we can do with that if we take that one step further. I have implemented here you see it, a bunch of types in order to be able to show you how you can build a completely different iterator. In my case, I want to implement an iterator which allows me to iterate over the rows of my board. Remember, I don't have a two-dimensional array. I have a single-dimensional array with just 9 elements in it. And I want to build an iterator, a virtual iterator, which iterates over rows which do not really exist. There is no data structure internally that has rows. So how can I do that? First, I implement a structure which is called row. This is a small data type which holds a reference, a pointer to the underlying board content and the row index, a pointer and an index. You might ask yourself what this funny thing is like. This is a so-called lifetime. It has nothing to do with traits. It is a different topic for a different talk. Just so much you need the lifetime here because Rust needs to understand that the row can never outlive the board content. That it cannot happen that you have a board in your hand and you already destroyed the underlying board content. In C# I could do that. And if I do that and I try to access the underlying content, things would go horribly wrong. In Rust, the compiler is smart. In Rust, the compiler has these lifetime annotations, and with that, it doesn't need a garbage collector, and it can still prove, mathematically prove, that it will never happen that you have a row that outlived the underlying data type. This is what lifetimes are all about. You can use lifetimes in traits, definitely. I will not go into the details here, but I just want you to be able to follow what I show here. So if you ask yourself, what is this? This is a lifetime annotation. I'm binding the lifetimes of these two things together. Now I have a bunch of implementations. That is not that interesting. I will go down here because now it's starting to become very interesting. Now I start to implement the rows iterator. The rows iterator is essentially an iterator which again holds a reference to the board content and the next row. And the interesting part comes here where I implement now the iterator trait, which is the standard iterator trait for my rows iterator. And the only thing that I have to in the background implement is the next method. This is how iterators work in the background. The system will just call next over and over again, and I can write my own custom business logic, and what I have to return is an instance that I will get back from this iterator. So if I run through the rows iterator, I will get one row instance, you saw it before, one after each other. I'm just maintaining a counter here, and I'm adding 1 to the counter whenever I call next. If I'm at the end, I just return none. If you are new to Rust, none is Rust's null. There is no null in Rust. Rust has the option type. And the option means either I have something for you or I have none. There is no possibility for null. null is not supported, at least in the safe Rust context. And we are not going to talk about this ugly, unsafe stuff, which we are not going to talk about that. That's a completely different talk. So you see, you can easily implement these iterators. Now, what does this give me? Let me quickly jump back to my board content and scroll down to a nice little piece of code which I have. Where do I have it? No, I'm in the wrong file. Here is this nice little code. This is what I was fighting for. See that one? For row in self.rows. Rows returns the iterator that you just saw. And because this is a system trait, my iterator is capable to work with a for loop. So by implementing this iterator trait, the for loop now calls my next method, and every call to the next method returns an instance of the row. And then I did the next interesting stuff. See that one? I'm able to index inside of the row by using this indexer down here. So the square brackets, and that will be the column inside the row. And that will be the next trait that we are going to take a look at, the index trait. But I hope you understood now that this is pretty awesome. And by having this iterator support, I get really strange things. I can, for instance, say, see that one? Hey, give me the nth row inside my board. This is a feature, this is a functionality that I get out of Rust's awesome iterator logic. You could do, give me, skip some elements, or take some elements, or filter some elements, or map some elements. And in this case, I just use the nth operator. This will give me the first, in this case, it starts by 0, so the second row, by just calling my next method 2 times and give me the second row. So by implementing this iterator trait, I open the whole possibility that Rust brings with its iterator library. Okay? And this is a completely custom implemented iterator. Nothing standard iterator stuff. It's completely written from scratch with my rows. Any questions so far? Good? Nice. I promised you indexing. I promised you indexing, and indexing is here. Let's do it that way. Okay. This one and this one. These are 2 additional traits that I want to talk a little bit about. The index trait enables us to access our data structure with the square bracket syntax. It allows us to build a custom indexer. The first one, you see it here, receives a reference to self, to board content, because this is the data type that I want to be able to index. And because it just says is a reference to self, it's a read-only reference. If you take a look at the index mutable down here, this is the second trait I would like to mention. You just write reference mutable self, and that means I can write into self, into my own data structures. And this is a deep immutable. That's not a shallow immutable, but if I have an immutable reference, I cannot manipulate whatever I have and whatever is inside of my own. Again, there is Rust magic with which you can allow certain things, but the default behavior is exactly like that. It's an immutable version of myself, and I cannot manipulate myself. So I can only return, as you can see it here, I can return an element from myself. But if I take a look at the index mutable, here I can return a mutable reference to an element of myself. Don't get me wrong, the index mutable is kind of interesting. It doesn't do the writing. The index mutable trait takes a reference which points to some data structures that I internally use and gives back to the caller a so-called mutable borrowed reference. So the caller gets a reference that the caller can use to write something into this memory. Understood? That is what index mutable is all about. And if you ask yourself, oh, Rainer, what can then happen with parallel, what can happen with parallel programming? Do I need to worry about some race conditions and things like that? No, you don't. Because the ownership and borrowing system of Rust protects you from shooting yourself into the knee. Yeah? The ownership borrowing concept is again a very good topic for another day, for another Rust Linz meetup. I'm not going to talk about it, but just trust me and believe me, if you build safe Rust, not unsafe Rust, you don't need to worry about parallel programming and about data races and things like that. These things are gone, they are no longer present. Without the garbage collector and without a heavyweight runtime. That's the awesome thing of Rust. That's the magic of the Rust compiler. Okay, so index mutable. Good. Yeah, that is not that interesting. I had some indexer and that's good. And last but not least, before we go into the last few minutes, I think I have, 10 minutes left or so, and then I'm done. Let's take a look at game. Game is another interesting thing. Maybe it's interesting, I'm not sure. I hope it will be interesting for you. What I did here is I had another idea for something that I can show you. Try to concentrate for the last few minutes here. You see, I invented, here you see it, a trait which is called square assessor. It allows me to access a square inside of a tic-tac-toe board. And I implement two different methods, get and set. I think it's pretty obvious what this thing does, right? Pretty clear, not very difficult. For those of you who are quick and who take a close look at my code, you will probably already have recognized something up here. See that one? Mock all, auto mock. Does that ring a bell to you? Of course we can use traits for mock objects for unit testing. And I will show you that in a second. This is why I implemented this trait. This trait is mockable. And this nice little crate is something different than a trait. Okay, for those who are new to Rust, the crate is like in C# a NuGet package, or in JavaScript an NPM package, or in Java, oh my god, I have no idea from Java. Maven? Did I say something wrong? No, not really, kind of. Let's not talk about Java. NuGet and NPM, I'm sure about that. A crate is the same in Rust. And mock all is a crate, a nice crate for mocking. And here I'm telling this mock all crate to auto-implement a mock object for my trait, which I can later on use for unit testing. Okay, you will see that in a second. But the second important thing here, you will see that here, is this line. I now implement the square assessor not on top of my board content, because I don't need a board content for that. I implement it on top of any data type that supports indexing via a board index. This was the save index that we built together, and that returns a square content. So if you want to build a data structure with a backing vector for your tic-tac-toe game, feel free to do so. As long as you allow me to index with my board index and you return a square content, I am fine. My game controller will still work on top of it. So again, an application where I implement the trait on top of another trait instead of implementing an interface on a concrete class or structure. Get it? Clear? Awesome. And with that, I can do crazy stuff. Something like, let's take this one. This checks a method which is called isValid. It just checks whether it can never happen that we have two X's and no O's. So a player has set 2 times and the other one has never set. Something like this is discovered with isValid. But in this case, I would like to implement, to test this logic of isValid without having a real board content. I'm using the mock version of my square assessor. You see it here? This struct mock square assessor was not created by me. This is the result of the auto mock macro that you have seen before. It took my trait, my assessor, my square assessor trait, and created the structure which is called mock square assessor, and I can then mock, for instance, the get method, and implement some lambda function here, which is called whenever the get method is called. And in this case, I'm just returning x then O, then x, then O, so this will be a valid board, so I can assert down here that is valid really returns true. That is my unit test. And if we take a look at the second test here, this is the error case. In this case, I make sure that this board is not considered to be valid, because in this case, I'm returning a given value, x or O, 2 times, and all other elements are empty, and that's not allowed. Because then x has shot 2 times, or O has shot 2 times, and the other one has never shot, and that is not a valid tic-tac-toe board. The business logic is not the point. The point that I want to make here is really the possibility of implementing traits on traits and of using traits for mocking. You might ask yourself, can I use structs and mock based on structs? Yes, that's also possible. So AutoMock allows you to build mock structs on top of other structs. That's possible, and in some cases you really need that. For instance, I do some work with the Rocket framework, which is a framework for building web APIs in Rust. I really like it. I've done a talk at the Rust Linz meetup about it, and whenever I have to do unit testing with mock objects, for instance, to mock away my database or backend microservices, I need to apply AutoMock on top of structs. Awesome. Good. You have learned a lot, and we are already nearly at the end, but I would like to show you one last thing, one last look behind the scenes. I would give you this magic sword that you just saw here. And I will not show you that in details because I have prepared it here in my slides. Come on, Internet, show me my next slide. Oh, isn't that nice? You can really read it very nicely. No, probably not, so I will zoom in a little bit. I want to show you what's going on behind the scenes when you implement some traits on top of a structure. Let me go up here a little bit, and then it should be readable. Hopefully it will be. Yeah, I think you can read it properly. Is that okay? I think it's okay. Please check that here I have implemented 2 structs, cat and dog, and I have implemented the trait animal. Now here I have implemented a function which takes an animal, and please recognize the impl keyword here. I essentially say the print sound method should be applicable to any animal. Anyone who implements an animal can call print sound. Now the interesting thing here in this last demo of my talk today is what's happening behind the scenes in assembler language. In assembler language, we get 2 different copies of our print sound method. The process here is called monomorphization. So it duplicates the necessary functionality in assembler language so that we don't have to pay with a dynamically dispatched indirect function call. We get a static dispatched function call. One version calls the dog, one version calls the cat, and of course, a statically dispatched call is really, really fast. So by calling, you see it down here again, by calling print sound with cat and dog, you see it on the left lower corner here, I do monomorphization and duplicate the code. So I get better performance, but I get a little bit larger code base. This is what's happening when you use this impl keyword. You cannot use impl always. In some cases, it's not possible. And then you need the second keyword, and that will be really the last keyword of my presentation today, and that is the dyn keyword, dynamic dispatch. That's essentially exactly the same code that you have seen before. The only difference here is that now I'm using here the dyn keyword. What I get from the dyn keyword is a so-called trait object. Technically, I get a kind of vtable, a table with virtual function pointers, and the method dispatching is done through the vtable. So in this case, again, I call print sound for 2 animals, cat and dog, but see it up here? It calls the print sound method in assembler language, and the print sound method in assembler language up here, I copied it out here, I don't have two print sound methods here. I just have one print sound method here. And this print sound method makes an indirect function call through the vtable. And of course that is slower, but I don't need a duplication of the methods here. I don't have monomorphizations. There are a lot of situations where you need this trait objects, and I cannot go into the details here because this is not a training, this is just a talk, and I limit myself to 1 hour. So I just can give you the facts, and you have to read up the details when you have to use trait objects and when you can use the impl keyword. The compiler will tell it to you. So if you try to use impl where it doesn't work, it will tell you use dyn. And if you use dyn and you use it in the wrong way, for instance, if you need to create a box and put the dyn in it, trust the Rust compiler. The Rust compiler will lead your way. You will love it, hopefully. Maybe you will hate it sometimes, but the Rust compiler is always right. It will guide your way. That's the beauty of the Rust compiler. Okay, that was a lot of content for 1 hour. But I wanted to give you an idea what traits really are, and that they are more than just interfaces. I think traits really rock. What are the most important things that you should take away? You should take away that traits are one of the underlying major concepts of the Rust programming language. Type conversion, operator overloading, iterators, everything is built on top of traits. You get zero cost abstractions through monomorphization, or if you don't need monomorphization, the traits, you don't have to pay for the traits at runtime. Yes, dispatching, dynamic dispatching is possible with the dyn keyword, but it's not a must. It depends on the situation and on your code. I hope you found this 1 hour interesting. I hope you enjoyed today's Rust Linz meetup. We are now pretty at the end of our Rust meetup. It's getting dark now. The video beamer now works perfectly fine. Before we go to the fridge and take a last drink and maybe talk a little bit, chat a little bit about what you've heard today, about your experiences, let me ask you, do we have any urgent questions that we should discuss before we get some additional drinks and eat the rest of the Ferris cake? Do we have any questions from the audience? Currently not? Okay. Okay. That's good. That's good. So I hope I didn't screw up, and I hope I describe it in a pretty understandable fashion. So with that, I think it's up to me today to close the streaming of the Rust Linz meetup. Don't get me wrong, the in-person meetup is not finished yet. We have some drinks in the fridge again, and we have a little bit of cake left, so stay here for another few minutes. Thank you for coming. I hope you enjoyed this in-person meetup. Thank you to the people on the stream now. Let me go here. Thank you for being with us. Thank you for being part of the Rust Linz meetup. And of course, we will put the recording up in the next few days. So if you hadn't have a chance to view it live, you can always rewatch the videos on YouTube. Thank you very much. Have a good night. See you at the next Rust meetup next month. Bye.